Alright, scholars, we're going to take a look at another statics example. So I've got my statics problem-solving checklist, and I've got number 13 from the Giancoli chapter. So this one says, let's take a look at it. It says, how close to the edge of a 20 kilogram table shown in this figure can a 66 kilogram person sit without tipping it over? So we've got a table which appears, we can double check, but it appears to have legs evenly spaced around it, and we're told that the table is massive. It's 20 kilograms. So the idea here, and maybe you've done this, maybe you've been sitting on a picnic table or something like that, and someone's too close to the edge, it'll eventually tip over. So we're going to just simply follow the checklist and see if we can figure this out. This time we're trying to solve for something very different than some of the other ones. We're trying to solve for the distance that they can sit near the edge such that it doesn't tip over. Alright, so we've got our drawing. I copied down everything from the question. Let's make sure we get masses and see if we can figure out anything else. So we're told the person is going to sit somewhere near the edge. Let's say they're going to sit somewhere like this. And we'll just say that they're going to sit a distance x from the end. We can work with that setup a little bit later if we need to. That person, we'll say the mass of the person is 66 kilograms. We're also told the mass of the table, I'll call that MT, is 20 kilograms. And then there's one other thing that we can figure out from this picture. If the whole thing is 2.2 meters across, and from here to there is 1.7 meters across, then we can do by symmetry that this is also 0.5 meters. In other words, these bits add up to 1 meter. 1 meter plus 1.2 meters gives us 2.2 meters. So again, we're wondering, where can this person sit? We'll give them a weight of mg, such that the table itself does not tip over. So, like a lot of these questions, it's hard to know exactly where to start. We just want to go and look straight at our problem-solving checklist. So the first thing we want to do is do our free body diagram, and we want to choose a direction for each force. Pretty straightforward. So one of the things to remember is that when something has mass, like this table, remember it's 20 kilograms, its weight is going to act right at its center of mass. So I want to be careful with my labeling here. The mass of the table, its weight is going to be mtg, just like that. And then and then this one is going to be the mass of the person, mpg. Looks okay. Zoom in a little so we can see that better. Okay. So one of the things we can figure out is that if this is directly in the center of this 2.2 meter tabletop, and this is symmetrical about the middle, then from here to this table leg is going to be 60 centimeters. That's going to be important shortly. I'll show you why that is. What we're also assuming, and this is where imagining the real world is helpful but possibly tricky, is we're going to imagine that this thing is going to rotate in this direction, the clockwise direction, and it's going to do it about this point. So I'm going to pick my pivot point right here. This is our pivot. If you've ever been on one of these sort of unstable tables, it usually will pivot about one of the two table legs. It's kind of arbitrary. I've just picked the right-hand side just for fun. Now, what we're assuming is that this person is sat at a location, we call that distance x, such that the table is just about to tip. So there's going to be no normal force here because this table leg is just like sort of magically hovering right above the ground. It's just about to fall over, just like if you push something with static friction, it's just about to move. Same concept. Now what's going to happen is that these both are going to push down on the ground, and then this table leg is going to push up. Make this red so you can see it. This table leg is going to push up with some kind of normal force. So this thing is pushing up, these both are pushing down about this pivot point, and we need to figure out where this person can sit so that the table just tips over or just doesn't tip over. So I realized I accidentally did step 2 of our problem-solving checklist. I chose a convenient coordinate system. I need to do a couple things. First, we don't need to break any forces into component vectors, but what I do need to do is I need to indicate what's up and down, we'll just say that this is up in the y direction, this is positive in the x direction to the right. Fairly straightforward. The next thing we need to do is set up our first condition for equilibrium. So that's the forces. So this example here, we don't need the sum of the forces in the x direction. There's no forces acting horizontally. All of the forces are acting in the vertical direction. So let's set this up. Let's do that very carefully. We want to do, starting with normal, because it's positive, minus the other two forces. So that would be mass of the table times g minus m of the person times g, and that all adds up to 0. Okay, next what we need to do is we need to set up the torques, and we actually already picked our pivot point. We also need to pick the directions, choose a positive and negative direction of rotation. So the sum of the torques is 0. Let's do this. We already picked this as a pivot point. Again, we're going to assume that the table is going to rotate about this. And so we'll call that the negative direction. Clockwise will be negative, and counterclockwise will be positive. And so let's set up our torques about this pivot point. Now we picked a smart pivot point because now this normal force doesn't act as a torque. It has no lever arm. Remember, torque is the distance times the force. Since there's no distance away from this pivot point, this normal force doesn't count as a torque. So our first torque, if we want to start in the positive direction, the counterclockwise torque, pardon me. So the mass of the table is going to exert a force down this way, which is going to be a torque of the lever arm of 60 centimeters, or 0.6 meters. So we can start there, since it's in the positive direction. So we've got mass of the table times g, that would be the force, times a distance of 0.6 meters, minus any other torques. We've got the mass of the person exerting a torque at some unknown distance x that we're trying to solve for. So that'll be mass of the person times g times x, and all of that is going to sum up to 0. This problem started out a little bit more tricky than some of our teeter-totter problems, but it actually boils down to the same math. Let me show you what I mean. We know all of this stuff. We know the mass of the table. We know the acceleration due to gravity, 9.8 meters per second squared. We know the mass of the person. We know gravity again. X is our only unknown. So it's going to turn out that we didn't even need to set up the forces, although it's good practice to get into. Let's go ahead and solve for X. Add the mass of the person and the acceleration due to gravity to the other side. So we'll have mass of the table times the acceleration due to gravity times the distance, 60 centimeters. And that's going to be equal to the mass of the person times g times x, the distance that we are looking for. So we can cancel the g's, which is nice, even though we knew them. And we can then divide by the mass of the person. So I've just rearranged that, and I'm going to now plug in the mass of the table. That's 20 kilograms times 60 centimeters divided by the mass of the person, which is 66 kilograms. And we end up with the distance x being 18 centimeters, 0.18 rounded, that's about what it is, meters. Now, we should always double check, quick gut check to see if that makes sense. So what we were saying is from our pivot point, which was this table leg, that the mass of the table, which is just 20 kilograms, a distance of 0.6 meters away. So it's lighter than the person, so we should expect the place that the person can sit from the edge of the table to be quite a bit smaller. So it ends up just being 18 centimeters. So that would be a smaller distance here, 18 centimeters. And it's reduced by about a factor of a third because the person is about 3 times heavier than the table. Hoping some of these more complicated looking examples are much easier with our spreadsheet. We set everything up. We ended up not needing to use the forces. But perhaps they would ask you a question like, what is the normal force or the force required by the table to keep everything balanced? That's why we sometimes will need to set this up. We'll see that in some other examples. Just realized that part of my drawing could be confusing, so I do want to clarify something, and we're going to make a slight edit to our original drawing. So this 18 centimeters means that the person can sit 18 centimeters to the right of the table leg, and it won't fall over. That's what this 18 or 0.18 meters means. So we should go back to our drawing. When I originally set this up, I sort of naively did this with respect to the end of the table. Now, we could have been kind of crazy and set the pivot point as the end of the table. We didn't do that, which was frankly pretty smart. So we need to actually change the way that this X is set up. We want to know where the person can sit, but we want to know where they can sit with respect to, just very slightly change our drawing. We want to know where they can sit with respect to the pivot point. So I'm going to go ahead and pause and show you what that should actually look like. So to clarify what our number at the end is saying, is the person can sit 18 meters from the end, which means that what we're really talking about is how far away from here can they sit, and we were saying that that distance was X. So their weight force would actually act right here, the mass of the person, MP, let's call it, times G. So there you have it. In other words, if the person is scooted any farther away from the supporting table leg, this whole thing would tip over in the clockwise direction. Hopefully that makes sense. Thanks so much. Thanks so much.